We're going to start with Module 3. Module 3's got some nice slides. We'll go through a few of them, and we'll switch off and look at my notes, and then just kind of work, number one, on the encapsulation model. That's really the goal of this particular lab. So if we kind of look at the slideshow and where it starts, it begins, and it's got these cool people, college students, obviously, because they are holding like really cool backpacks and like messenger bags. And they're saying, hey, well, you know, what we're trying to learn here is communication skills. And when we want to communicate between a computer and another computer, there's going to be some rules that go along with it. There's going to be some media that the information is going to pass along through. And in the end, everyone's going to be able to connect with their neighbors. So that gets us into the next slide, which talks about the idea of rules establishment, and that there are governing bodies that are used or have been established to speed up the process. And we'll do another video on that in just a few minutes, because that's really a little bit further down in the PowerPoint presentation. And then the next thing it talks about is the idea that the devices have to be in agreement for the encoding of the message, the formatting of the message, the size of the message, how fast the message is going to get delivered, and the different options that may be available to be used to make that happen. And all of this has been pretty much furrowed out. You know, in the 80s and the 90s, there were a lot of different really science projects on, hey, what method should we use to pass data from one place to another? And different organizations had different ideas on how they would set that up. And really what's ended up happening is most of the best practices have really just kind of overrun all of the scientific experiments that didn't totally work out. And what we're left with is something called TCP/IP, and there's really two versions of that. There's IPv4 and IPv6, and TCP/IP's favorite method to be passed along across a media is copper wires, even though there's other types. There's fiber optics, and the other piece that fits in between those two is an Ethernet header, or the concept of how Ethernet will pass traffic in a local area network, and that'll get us into how MAC addresses work. Long ago, I'll tell you a quick story. I worked for a company that was putting in network cards for a big organization in Northfield. And so we went into Northfield, and they had all of these computers, and at that point in time, the easiest way to make a computer networkable was to take the side of the computer off, put a network card in it, and run the drivers, and you could then be part of a network. And so what we did is they had, I don't know, a couple thousand computers, and we put in a couple thousand network cards, and we connected them all into a network, and that network was known as a token ring network. And a token ring network is like Ethernet, or is comparable concept, but it would max out in speed at 15 megabits per second. Previously to that, they had network cards that could go as fast as 2 megabits per second. So the upgrade from 2 to 15 was tremendous. It was a tremendous innovation. So they said, okay, we're all in on token ring, and they had these token ring switches and token ring network interface cards. And we put all this stuff in, and then a year later, we went back and we took all the token ring network cards out of all the machines. We removed all of the token ring switches, and we went to a new form of Ethernet called fast Ethernet. And that fast Ethernet could run at theoretical 100 megabits per second, as opposed to 15 megabits per second. So much faster with the new solution. And we took all the token ring cards out and all of the token ring switches out of the system, and we replaced them with fast Ethernet network cards and switches, and everything worked, and it was a really good project both times. It was easy to be employed to do that much work. So a little story about physical topologies, which is really chapter 4, and just to kind of give you an idea of the pieces and parts that are involved in making a network go. So the next thing the PowerPoint communicates about is message encoding, and the idea of encoding is basically this: is we've got this stuff that we want to send, and we're going to have to prepare it before it can be sent on its way. And there's a couple of things you're going to need to do. Now, one of the first things you're going to want to do when you've got a message of stuff that you want to send is you have to figure out how much stuff can you send at one time. So just like in any case, you might have written like a novel, like you wrote Moby Dick. It's a really long book. If you remember books, and that's a lot of paper, and you want to send it to your publisher, but you don't have enough. I don't know. You can't put the whole thing in one envelope and send it along. The postal system will say, "No, this doesn't really fit our needs." So what you're going to want to do is take a few pages at a time and plug them into each envelope, and then address them each time, and then have some kind of method where you could identify, well, this is the first few pages of the novel, and then this is the next set of pages of the novel, and so on and so forth. And this would be something that you would have to do if you wanted to send a book to somebody else, letter by letter, because that would fit the postal code's model of how much you can send. Well, the same thing is true with data transmissions. When you have information that you want to send, if there's more data than you could send at one time, and we'll get into that in just a little bit, you're going to have to create what's called a PDU, or protocol data unit, and send part of the data at a time. And when you send part of the data at a time, each piece of data that you want to send to the receiver has to have some addressable components. So those addressable components that are needed are things called, there's something called a port value, and the port value is just a value that you would use for the receiving device to figure out what application should be used to read what it is that you have sent in the data section. So I'm going to kind of pop over and switch out of the slides for now, and I'm going to pop into my drawing utility. And in the drawing utility, I'm just going to take a look at where we are there. And really, these are my notes. Starting off with, these are the notes that I've written for this particular chapter, at least this section of the chapter that we're going to cover in this video. And this just talks about the communication process and really the encapsulation model. So what I'm going to do is I'm going to go ahead and write that out, and I'm going to identify some of the values that are necessary for sending information. So remember, in the encapsulation model, we have a section called the data section. And the data is just the stuff that we want to send over to our neighbor device. And then we need to add another value in a header called the segment header, and any device that is participating with TCP/IP is going to be able to identify what a segment header is. It's usually formatted as TCP or UDP, and we'll get into the differences of those later on. But for now, the segment header is going to maintain two values. It's going to have what's called a source port, and that is the application or process that generates the data. And then there's going to be another value called the destination port. And the destination port is going to be the port that's going to be used that's associated with the receiving application so that the data can be turned into something useful when it gets to the other side. So just as an analogy, everyone has opened up a Word document before. And you all know that the extension of a Word document is .docx. And if you tried to open a Word document in Excel would say, this is not really formatted for me to display to you, because Excel uses a file extension of .xlsx. And that additional file extension value tells the computer which application it should use to open that particular set of data. And then there's some data that can be opened by different types of apps, but I'm getting off my point. The main thing here is this, is that the segment header has a source port, which is the process that created the data, and it has a destination port, which is the process that's associated with on the receiving device to turn the data into something useful on the other side. Simple enough, okay? And we'll get more into ports later. Now, the other addressable components that need to be added to the data section in the encapsulation model are IP addresses, which are held inside of the packet header. And I'm just going to write source IP and destination IP. I'm just going to write dest IP. You can figure out that that's destination. So IP addresses are necessary and used when we're going to pass information off of one network segment into another network segment. It's kind of like mailing a letter from your town to another town, and the zip code is used to identify, oh, hey, this isn't going to be delivered out of this post office. We have to send it to a different post office. Kind of think about network segments in that vein, more of a global address value inside of the packet header. There's more stuff in there, but the most important part is the IP addressing information. And then there's a third addressable component called a frame header. And the frame header has source MAC address and a destination MAC address. And this is more like a local address or familiar address of where something's located within the same segment. So I've kind of tried to write this out for you here. If we look at our notes, you see, there's three values that identify source and destination for each: the MAC address, the IP address, and then the port value. Inside the model, it does have those three headers: the frame, the packet, the segment, and then, of course, the data. And everything's written in here. And then the other thing that I wanted to identify in this particular video is the fact that the size of this, you might not be able to send the whole thing. Once again, you just wrote Moby Dick and you want to send it to your publisher. It's not all going to go in one envelope. So if you look at the whole size of this, it's only going to be about 1,500 bytes total. And that's because the way that systems are built or were built a long time ago is they could even the worst system in the world could handle a 1,500 byte protocol data unit. And what they found was it's better to send something and not break it up in transit than it is to send something that's way bigger and have it go fast for a while and then have to break it up into smaller parts to get it to its destination. So the lowest common denominator of any data solution that we could pass across was about 1,500 bytes, and that's the size that we send everything at right now. Now, does that mean in the future we can't send more than that? No, absolutely not. And if we had a closed system where we knew that our senders and receivers could have datagrams or protocol data units that were 10 times this size, we could send a lot more data. So our data section could be huge. We could have 10,000 bytes or 100,000 bytes. That seems like a lot. 100,000 byte data section with one addressable segment, packet, and frame header, which aren't that big. They're only, the frame header is usually about 14 bytes, and a packet header is 20 bytes, and segment header is usually around 20 bytes. But we could send giant datagrams behind that. That would give us less overhead, and we'd be able to send fewer packets, and everything would happen faster. So you'll find that there's certain networks that are out there that can actually send things quicker because they can use larger datagrams. But as far as we're concerned, in most cases, if you're going to send stuff across the internet, you don't know all of the media types that you're going to have to cross. So your systems will send about 1,500 bytes at a time at the most. And after that, they've got to segment things off and break them into smaller pieces. Okay? So this slide or this presentation, just a little bit about the encapsulation model.